Hello dear students, welcome to Tejama YouTube channel. So in this session we are going to discuss about two more important concepts, that is continuous charge distribution and the electric flux. In electric flux we'll talk about what is electric flux, what is the formula for electric flux, and there is very important law called Gauss law. Okay, so we'll go one by one. Here we have the charge density here. So how to find charge density in case of linear charge distribution, surface charge distribution and volume charge distribution. Okay, so let's consider here we have a line charge. So I can consider a huge number of charges present or distributed uniformly on a line or a wire like this. I need to find out the charge density here. For that I will take a small length. Let's take dl. So in it I can consider the charge dq. So here the charge density is given by charge per unit length, that is q by l, or in terms of dq and dl you can write lambda is equal to dq by dl. Okay, so dq by dl. Clear? So what is the SI unit for this? Since we have charge by length, for charge it is coulomb, length it is meter, so coulomb per meter. Clear? Next, what about surface charge density? Let us consider we have a surface here. So charge is distributed uniformly on it. Charge is distributed uniformly on it. Like this. So how to find out the what is this charge density on it? Let's take total charge divided by total area, or if you want to calculate the charge density for small area you can take dq by dA, and for volume charge density you can take a three-dimensional diagram like this. So in it there will be huge number of charges present but uniformly distributed. Here the charge density is given by rho, that is given by dq by dv. A small volume you can consider in it. So dq by dv will give you the volume charge density. Clear? So what about the unit? For surface charge density it is charge per area is there, so you can take coulomb per meter square. For linear it is coulomb per meter, so area coulomb per meter square, and similarly we have volume charge density, that is coulomb per meter cube. Okay, next we have the concept of electric flux. So what is electric flux? Here we have the area given. Let's consider this is some area, and perpendicular to it let me consider area vector. Area vector. Area vector. So with respect to this area vector, how the field lines are moving through it? Let's consider electric field lines passing through it and coming out in the direction of area vector. Then what will be the theta value? The angle between electric field and area vector is given by 0 here. If you consider, let's consider electric field is perpendicular to area vector, so then theta will be 90 degree here. So here in this case electric field is, just a minute, electric field is parallel to the surface, that means perpendicular to area vector. Here what is the flux? Or if I take some other angle other than 0 and 90 degree, let's consider some theta here less than 90 degree, how to calculate the flux? Okay, so we need to take that theta with respect to A. So the flux is given by the formula in simple, that is phi is equal to E into A into cos theta. E into A into cos theta, that can also be written as E dot A. That means electric flux is a scalar quantity. Clear? Scalar quantity. Then how to define it? So electric flux is defined as the number of field lines passing normal to the given area. Number of electric field lines, see here it is given. Number of electric field lines. So field lines of force also we can call. So crossing surface normal to it, normal to the area. So or you can write number of field lines passing through the given area normal to it. So that is called electric flux. So that is given by this formula. Clear? This is one thing. Then, sir, I want this in differential form. So yes, I can write it in differential form also. If I consider a small area here, dA or ds also we can write, surface area ds. What is the flux passing through that? Can be written as small flux d flux, that is d phi, is equal to E as it is into dA we have to write. In vector form you can write dot product here. And if you want integral form, that is the total flux can be written as E dot ds. You can write dA or ds, it's up to you. This is for open surface. For closed surface we write the closed symbol here. This is for closed surface. So this is about this. Then what is the SI unit of electric flux? Since we have E and A, for electric field the units are Newton per coulomb or volt per meter, and for area it is meter square. Okay, sorry, meter square. So if you multiply these two or these two, you will get the SI unit of electric flux as Newton meter square per coulomb, and voltmeter also is the unit for electric flux. And then what about dimensions? It is m1, L3, t power minus 3, a power minus 1. Sir, can we derive this? Yes. Let me derive the dimensions of electric flux. So here, let us take, we have phi is equal to E into area. So for E, can I write force upon charge? Yes. And area, I can write it as area only. Force unit is kg, meter per second square. So you'll get m power 1, meter means L power 1, per second square t power minus 2. Area meter square, that is L power 2. And charge is given by current into time. You can write like this. So m power 1, L power 3, t power, in the denominator 1t is there, t power minus 3, and current ampere power minus 1, which is there in the denominator. So that's why this is the dimensions of electric flux. Clear? This is about basics. So when do you say flux is maximum and when do you say flux is minimum? So let us discuss about this. The flux is maximum when the electric field is normal to the given area. If I consider here, electric field is normal to given area, that means in the direction of area vector, then theta will be 0 degree. Then we can take the flux phi is equal to E into A into cos 0. Since cos 0 is the maximum value, that is 1, then flux will be maximum. So flux maximum is given by E into A. So cos theta will not be there. So when do you say flux is minimum? Flux will be minimum when electric field is parallel to area. So when electric field is parallel to area, so you can take in this direction, then the area, this angle between area vector and electric field will be 90 degree. So the flux is given by E into A into cos 0, sorry, 90 degree. Cos 90 is, value is 0, therefore flux will be minimum. that is phi minimum is equal to 0. And then for a closed surface, sir, I have a sphere here. If the field lines enters into the sphere and comes out of it, then how to find out the flux? See, for a closed surface, flux will be 0. The net flux will be 0 for the closed surface. But if you want to calculate the flux in and flux out, so flux out is always taken positive and flux in is always taken negative. This will be important for your competitive exam point of view. Clear? Yes, let us discuss about this. Next we have a law based on electric flux, which is very important. That is called Gauss law in electrostatics. According to Gauss law in electrostatics, the total flux through a closed surface is equal to 1 by epsilon times charge enclosed. That is given here. The total flux linked with the closed surface is equal to 1 by epsilon times charge enclosed by the closed surface. So the formula is given by this q by epsilon naught is there, where q is the enclosed charge. What does it mean? Let's consider there is a closed surface here. I need to draw. Okay, closed surface. Here we have charge q1, q2, minus q3, q4, minus q5, like that. So what is the enclosed charge? Enclosed charge is q, that is equal to q1 plus q2 minus q3. So this part, it depends on only enclosed charge, but this electric field depends on all the charges. Electric field depends on all the charges, but this right side part q by epsilon depends on only inside charges, inside the surface, given surface, where epsilon naught is absolute permittivity whose value is 8.854 into 10 to the power minus 12 units. You can write farad per meter, or in terms of Coulomb force, or also you can write in terms of Newton. Okay. Next, this is very important statement. Do remember. Based on this, we have some applications. Okay, we have derivation based applications also. About that we'll be discussing in the next session, or I will share the link to those derivations in the description for this video, so you can please watch them and practice the derivations, which are very important. So we have like electric field due to linear charge, that is E is equal to lambda divided by 2 pi epsilon naught into r, and we have electric field due to thin sheet, that is sigma divided by 2 epsilon naught, and we have electric field due to sphere. There we have two different cases, that also you can practice. But as of now, we have some basic applications. Look at this. If a dipole is enclosed by the surface, the charge enclosed will be 0, because here dipole consists of one negative charge and equal positive charge. What will be the net electric charge inside the surface? 0. Then the flux through the surface is also 0. Very important one for KCET exam point of view. Next, if the charge q is kept at the center of the cube, let's consider here there is a charge q. What is the flux through the cube? The total flux get distributed through 6 surfaces of the cube, like this. The total flux is given by q by epsilon naught. And if you want to calculate the flux through each phase here divides equal charge. What is this flux here? Like this. Each phase flux is given by q by 6 epsilon, because the cube has 6 faces. It has 6 equal faces. Correct now? So flux also get divided by 6. Then what about the flux through each corner? How many corners are there? 8 corners are there. So q by 8 epsilon naught. And edges, so actually this will not be asked much. Flux through edges, 12 edges are there, you can just divide it by 12, but most important thing is this one, face and cube. Moving on to next one. If the charge is kept at the center of the face, let's consider there is a charge here on the face, then what will be the flux through the cube? The flux through the cube is given by q by 2 epsilon naught, but here it is given flux through the total flux through two cubes. Okay, what they have done here is they have imagined, just a minute, let me erase this. This is not 2. Okay, yes, here what they have done, they're drawing a cube, one more cube here. Okay, and then take the flux through both the cubes. Here half of the flux enters this cube and remaining half of the flux enters this cube. So the total flux emerges from the system is q by epsilon naught. That is correct. Actually here I have written small q, you can write capital Q because in the formula we have capital Q. Okay, but what is the flux through the given cube? That is q by 2 epsilon naught, because the flux is getting divided into two parts. And what about the flux through each face? You just have to divide it by 5 because you have to neglect one face. This face you cannot consider here. Do not consider this face. Remaining 5 faces will be there because here the flux is parallel to the surface. So theta is 90 degree, cos 90 is 0. Okay. So if you consider the charge on the face, the flux will be parallel to that face. So E into A into cos 90 degree is 0. Clear? Next, look at this. Here we have, if the charge is kept at the edge of the cube, then what will be the flux through the cube? This question was given in KCET 2026 also. Recently I have just solved it. The charge is kept at an edge. Okay, what will the flux through the cube? Since to this edge we can attach, look at this, 3 more cubes, so that means the flux get distributed to 4 cubes. So you have to write flux, total flux is q by 4 epsilon naught, but through each cube flux will be divided by 4. So, I mean 1 by 4th of the flux to one cube, so like that distributed, so we have to divide it by 4. But what about the faces? Here you should not consider two faces. This one don't consider and this one don't consider, because flux is parallel to those two surfaces. Remaining how many surfaces will be there? 4 surfaces or 4 faces. So divide this again by 4, you will get 4 4 is 16, that is flux through the face is 16. Clear? Next, applications of Gauss law. In that we have one more case where the charge is placed at the edge. If charge is placed at the edge, so to that edge we can attach how many cubes? 8 cubes, like this it is given in the diagram. So flux, total flux is q by epsilon naught, but through each cube the flux is getting divided 1 by 8 times, so that's why q divided by 8 epsilon naught. So in that 3 faces you should not consider because it is attached to this face and that face. Remaining 3 faces will be there, so opposite, then you have to divide it by 3. So q by 24 epsilon naught. This is very, very important because this was asked in NEET as well as KCET. Next, what if we have linear charge? So here, actually this is NEET and JEE level concept. Even if they ask in KCET also, you should be in the level to answer. Let me consider, here we have charges. Just a minute, the laptop is getting charge. Okay, now here we have the linear charge. Okay, linear charge, so of infinite length, but this wire is having the charge density lambda. So calculate the flux through the cube. So for that you just have to calculate the charge enclosed by the cube here. How do you calculate the charge enclosed by the cube? We know that lambda is equal to q divided by length. What is the length of the diagonal? So here the side is given by a. The length of the diagonal is given by root 3a. For the cube, length of the diagonal is given by root 3a. So that is q is equal to root 3a into lambda. This is charge. Now what is a flux? Flux is given by q by epsilon naught from Gauss law. What is q? Root 3a lambda by epsilon naught. So next case here, if I consider the linear charge distribution in it of density lambda, how do you calculate the linear charge density? That is just total charge divided by length. Length is 2 times the radius. Okay, so that is diameter. Q is equal to 2r lambda. Therefore flux is given by, flux through the sphere is given by charge per length, that is 2r, sorry, here it is given charge per epsilon naught. So charge is 2r lambda divided by epsilon naught. So these two questions are very, very important for competitive exam point of view. Okay, next we have, yeah, flux in, flux out and net flux through the cone in the below cases. In this case the flux is entering downwards from the upper face to lower face. If you observe from upper face, so here the area vector is in this direction. Let me consider small area vector. The area vector is like this. This side small area vector is there. That will be like this. So now if you take the resolution of vector, if resolve the vectors, the area, the resultant area will be equal to this area. What is the area of the circle here? Pi r square. You can take the radius r. So this area is given by A is equal to pi r square. So flux in is taken negative. Okay, negative. E, electric field is E, into area is pi r square. So flux out is written as positive E into area is pi r square. And net flux will be flux in plus flux out. That will be always 0 here for the closed surface. Now here the cone, if you observe from the sideways, it looks like a triangle. Yes or no? So let us take the height of this triangle is h. Okay, and radius is r. Radius is r. The flux in is given by minus E into area of the triangle is half into base is r into height h. Half into base is sorry, area of the triangle here, like the two triangles are there, this side also. we can take h into 2r. Just a minute. Since this is half into base is 2r. Yeah, correct. So we'll get minus E R H. And then flux out, same answer, plus E R H. Okay. The net flux will be 0. Clear? Flux in plus flux out. Then here we have hemisphere. So how do you calculate the flux in flux out? Same, you just have to consider area here. So area of the base is pi r square. So here flux in, you know, to take curved surface area here because the angles will be different. You can take flux in is equal to E into the bottom surface is pi r square, and flux out, same answer with positive sign, E into pi r square, and net flux is 0. Similarly, you try solving this. If you get an answer, please text in the comment section. Okay, shall I move on to next one? Yeah, so here we have some question based MCQ based questions. Let us solve them. A point charge Q is placed at the center of the cube of length L. The electric flux emerging from one phase is one phase means by 6 epsilon naught. Just now we have learned that is Q by 6 epsilon naught. Okay. Next one. If the radius of the Gaussian surface is enclosing the charge is halved, so how does the total flux changes? It doesn't change. Flux doesn't depends on the area of a closed surface. Okay, so it remains unchanged. If charge Q is enclosed by the Gaussian spherical surface of radius r, if the radius is doubled, so outward flux doesn't vary, remains same because flux doesn't depends on the closed surface area. Okay, here we have the field, electric field in the region is given by this one, E is equal to 3 by 5 E naught I cap, 4 by 5 E naught J cap. The flux of this field through a rectangular surface area A in the Z X plane is, let's consider Z X plane. So that will be like this. So this is X axis. This is Z axis. Okay, upward. This is Y axis. Okay. Now area vector will be in which direction? J cap. So we have electric field E. Okay. So let's consider this is in vector form. E is given. So on so. Now how do you calculate flux? Flux is given by E dot A. E is 3 by 5 E naught I cap plus 4 by 5 E naught J cap dot, what is the area? J cap. So J cap into J cap is 1, J cap into I cap is 0. So this, if you multiply, becomes 0. Only 4 divided by 5 E naught into A will be there. So 4 divided by 5 E naught A, that is option 1 is correct. Clear? Next, Gauss law is valid for any closed surface. Okay, option B is correct. Next, if the charge Q is placed at one corner of a cube, then flux through each cube is, since the corner is attached with 8 other cubes, so you can just divide it by 8. Option C is correct. This I have given in the synopsis. Next, electric flux through closed surface depends on net charge. So that is from the Gauss law, because phi is equal to Q by epsilon naught. So option D is correct. What about shape? It doesn't depends for the closed surface. Okay, size of the surface, no. Position of the charge, no. Okay. Hollow cylinder has a charge Q within it. If the flux is phi is the electric flux in the units. associated with the surface. The flux linked with the plane surface is, let's consider here, hollow cylinder has a charge q. Then flux is given by q by epsilon naught. Okay, total flux. That is equal to flux through curved surface area. So there will be two curved surface area in the cylinder plus one curved surface area, two end surfaces. Clear? So if I consider the cylinder here like this, we have two end surfaces and one curved surface. Correct? No? If phi is the electric flux in voltmeter associated with the curved surface. Okay, this is the curved surface. Which one is that? Phi. Let me consider this is total flux total. So q by epsilon naught is equal to, through curved surface area it is given phi plus 2 times phi end surfaces. So we'll take this one this side. So q by epsilon naught minus phi. So 2 will come down, 1 divided by 2 is equal to flux through end surface. So they're asking the flux linked with the plane surface or end surface is. So that is 1 by 2 q by epsilon naught minus phi. Next, a hemisphere of radius r is placed, hemisphere, okay, in the uniform electric field parallel to its axis. The flux through the curved surface is. So parallel to its axis means we can consider here flux through the curved surface, right? Curved surface 2 pi r square. Option A is correct. The SI unit of surface charge density is coulomb per meter square. Option B. Okay, this is about this video. So I have tried to complete it in a very short video. So if you want detailed explanation even more, please let me know in the comment section. I will try to make more detailed videos. So as of now, this is for KCET level. I have given short and simple synopsis and explained few questions based on it. So keep learning. If you feel the content is useful, please share it to your friends who are studying for KCET 2025 27 examination. Thank you so much. Signing off.